software for the analysis and the comparison with the behavior of the user in a different period. I want to highlight that in that period it follows also the one where we had the COVID emergency, and you can also observe, it's interesting to observe the change in the behavior of the user and in terms of water consumption during the different months. And that's all, and thank you for your attention.
Thank you very much, Salvatore, for your nice presentation and very informative on the capabilities of this software. So we have time maybe just for 1 or 2 questions from the audience. So you can use the chat or just raise your hand and we can give you the floor. So ask a question.
I saw John Rostum raised hand.
Okay, so please go. John, you are muted, so maybe try to unmute yourself and ask your question. So I think he has some problem of asking question. You can write your question in the chat if you have some audio problem. And maybe I will take this opportunity to ask a question, Mr. Salvatore.
Yes.
Regarding this software capability, I saw that you can manage to get data or track data for a number of users. Is there any limit for this?
In our test bed, there were only one user in the apartment, so it was the only one that consumed the water, that used the fixture. For the test bed, there is not a limit. Of course, there will be a complexity in the analysis because in the raw data, when more users are monitored, you have a superposition of consumption, and some works Anna developed about the disaggregation of total consumption. But I think that the availability of this kind of raw data that are extracted from one user and the utilization of this technology, artificial intelligence technologies, helps to overcome those issues which are related to aggregated data consumed by more user, to distinguish to extract the different, to discriminate different features. Where you see different users, that is the simulation of a larger scale, and in that case, you can replicate the same behavior of the same user. Okay, you can merge different profiles and variate the composition in terms of the heterogeneity of your sample.
Thank you very much. So maybe on this, I would like to thank you very much for your presentation, and we move to the next speaker. Our next speaker is Dr.
I saw also Mohit Kaushal raised hand.
Sorry?
I saw another raised hand, Mohit Kaushal.
So we may give the opportunity to another one for the question. Mohit?
Hello.
Yeah, now we can hear you. Yeah, please, Mohit.
Hello, everybody. My question is about: is we use this software commercially? If yes, how we link this software with our uh, AMI ready pro meters?
I understood the first question. The license is JPL. It means that you can use it, and if you made some changes, you have to release your own your software with the source with the changes. About the commercial usage, you can it's not an Apache license, but you can ask directly to release the software. So the you cannot sell, but you can use it if you release the source once you upgrade or change it. Can you repeat the second question?
The second one is, if yes, I want to link the kind of software that you develop with our society's AMR meters, to trace all their consumptions, as well their daily usages, and based on that, make trends about their usages of water, the kind of thing.
Yes, I assume you can do this. I do not see any concern.
Okay.
Okay, thank you so much.
Thank you, Mohit, for your question.
Welcome.
Maybe to respect our schedule, we will move to the next speaker. And if there are any other additional questions, so they can be put on the chat and we can save them and we can continue communication with the speaker later. So our next speaker is Dr. Jun Seok Lee. He is Associate Professor of Civil Engineering at Manhattan College. He is registered professional engineer of civil engineering and board certified diplomat from Water Resources, from American Academy of Water Resources Engineers. He currently serves as associate editor and editor board member of ASCE Journal of Water Resources, Planning and Management, also AWWA Water Science Journal and Frontiers in Water. He's also fellow of Environmental Water Resources Institute, where he received in 2021 the Profession Award. His research focuses on building water systems and water infrastructure analytics. Dr. Lee presentation title is Spatiotemporal and Machine Learning-Based Time Series Assessment of Drinking Water Quality Complaints in the US. So please, Dr. Lee, the floor is yours.
Okay, can you hear me fine?
Yeah, perfect.
Okay, great. Thank you very much. I appreciate it. So, okay, good morning, good afternoon, everyone. So, okay, it's a very great pleasure to have a talk this today. So the title of the talk is, as mentioned, spatial temporal and then machine learning based time series analytics in for drinking water quality compliance in the US. Right now, I know that the overall theme is water sensors. And then today, this title, this project is, we are using human as a sensor. So people complain about their taste and odor or colors or something's not right in their drinking water, then they report to the government. So we collected those data and then did the analysis for that. So human is basically the sensors in our study. And I'm glad that we have a lot of very good colleagues in here and also co-authors, including Anna, Salvatore, and Armando, and also Giovanni, all excellent colleagues as a co-author in here. I'm very happy about that. So go to next one. Okay, so this is in US. In US, every 4 years, we publish it, America's Water Infrastructure Report Card. And then up until 2017, the drinking water, including infrastructure and pipeline, the overall letter grade was a D+, which is absolutely positively the failing grade. And then the recent one, 2021, I'm very happy that it is C-, which is also the still the borderline of the failing grade. But there are still lots of things to work on related to our drinking water and drinking water infrastructure. So, and also just as a small background, I believe our water treatment plant quality is very good and supply the very good quality of water. But since 2000 or so, people, as you all know, we start to realize that there's something going on in water transmission or distribution phases because of the leachings or leaking and or contamination intrusion in our drinking water, which can deteriorate our water quality itself. And also what we start to realize, say 2010 or 2015, is within premise plumbing or building water distribution systems, we're starting to see significant water quality deterioration in our building water system. Why? Because since 1970s, people have been very concerned about the sustainability or water conservation or water efficiency very much. So overall, we haven't seen very much successful water quality, water conservation efforts. Overall water use has been decreasing very much. That's a very good success. But in terms of a water age or possible biological deterioration, such as Legionella, pneumophila, or different types of microbiological or pathogens, they have a very good opportunity to grow or proliferate within our drinking water systems, especially building water systems or premise plumbing, because it has a very high water volume ratio, and then diameters are very small, and also the water stays there pretty long, and then very good possibility for, again, deterioration. So now, that's why this project is focusing on the customers or decentralized water infrastructure or building water systems, and then utilizing people as a sensor. Okay, now, as you see in here, here's some of the snapshot of the open access data. So, for example, if you see the left-hand side, there's a Baltimore City 311 service. So 311 service, since say 2010, it has been pretty active. So if whatever they have a problem, the citizens have the problem, they call 311 or report via 311 website. And then if you see here, here's the some of the reported water quality related complaints. And also we have in this study, we focused on NYC data, New York City data. So we have about 15,000 of complaints for a few years. And then based on that, now we are proposing to perform spatio-temporal analytics in terms of a space and location. What's the trend? What are the hotspots? What are the emerging hotspots? What are the continuous hotspots? So that'll be, I hope that will be very helpful to the water utilities. Yes.
Thank you for your work.
I'm sorry. Okay. Can I move on? Okay.
Yeah, please continue, please.
Okay. So space, and also based on these very good data, which is actual data, we are proposing to apply different types of machine learning to find the hidden trend or hidden patterns and also make a forecasting. And then hopefully that will be also useful for the water utilities in terms of their planning, operation, and management for the near future. Okay, now, so if we go to, so the objective is, as mentioned, so perform spatial temporal analytics of observed water quality complaints, and then identify continuous hotspots, and then develop machine learning and deep learning based time series models to forecast water quality complaints in different cities, say New York City, Baltimore, Maryland, and Kansas City in Missouri. And then we're going to compare the performance of a machine learning, deep learning time series models, and then have a better understanding of different types of machine learnings, its capabilities, and also its limitations. And we want to make useful analytics-based recommendations for water industry. So as mentioned in the beginning, we have sensors, although we are using people as sensors, and also they're very good computational capacities. And then as you all know, the water industries, there are lots of room for improvement in utilizing data analytics, and then make an informed decisions in their daily operation and management. Sounds good. So the next one is just showing you descriptive statistics. So these are the NYC that are composed of 5 boroughs. This is showing Manhattan, the Bronx, and then Staten Island, like that, Queens. And then these are showing monthly number of water quality complaints. This is a time step of 1 month. So we collected almost 12 years of data. And then New York City residents reported over 17,000 taste and odor water quality complaints in between 12 years using NYC 311. So this is purely based on actual reported data. And then I'll talk about it more, but in the end, we're also planning to expand our current research by including Twitter data and then Facebook data by deep language-based, text-based, machine learning-based ones. So we want to augment or increase the data size, but right now this one is NYC 311 data is what we're reporting today. So this one is in another the plot for Kansas City and then Baltimore for each year. So it shows you some idea about how the spatial and temporal changes are happening for drinking water quality problems. Whenever I have a communication with the water utility directors or the managers, these water quality complaints, it's a really pain in their neck for the water managers, because then they have even 2 a.m. in the morning, 3 a.m. in the morning, if there's a problem, they let the crews go outside and then solve the problem. So how we can solve this problem? And also the good thing is for the citizens, it's all transparent, but for the managers, the data is there, so it's their responsibility. So we'll have to solve the problem together, right? So, okay. So now, as mentioned, so we're proposing to utilize spatial temporal hotspot analysis and then different types of machine learning, say, for example, LSTM, long short-term memory, and then neural network or nonlinear autoregressive neural network, and then very famous SVM support vector machine, another very famous Aleph or random forest. And also we today we are not reporting, but very classic time series models such as ARIMA or SERIMA. Those are what we considered. And then I'm not going over all the details about the equation, but LSTM, long short-term memory, is a type of machine learning, learning the sequential and then temporal patterns of a sequence of data, such as time series data. So we're proposing to use historical 311 water quality complaints data to train and test LSTM models to forecast future water quality complaints for each boroughs and also for New York City as a whole. The next one is a neural network or nonlinear or regressive neural network. In a very similar vein, we're again proposing to use water quality complaints data to train, test neural network to forecast future water quality complaints. So it's basically, as you see, this very simple formulation. So for next one is a function of the historical data, and then we are building the model using under the framework of neural network. And then the next one is a famous SVM. Again, we're developing a forecasting model. And then again, these are some of the fundamental governing equation for SVM. But we're finding the optimal hyperplane for linearly separable patterns. And then again, in layman's term, we are making a forecasting for the near future based on historical data. Lastly, we're using the random forest. And then these days, too many papers, many papers are for utilizing random forest in every domain, as far as I know. So it's been a general purpose classification and regression method. It has been very successful. And then we're proposing to utilize random forest in terms of forecasting and utilizing our time series data. So here's some of the result. So this one is considering within cells of a 2000 by 2000 feet block, and then we consider the number of complaints in each block, but at the same time in z-axis we also considered in each year. So these red cells clearly show that there is a higher density of a complaint, and also it shows that each year it is increasing or continuously showing higher number of customer complaints. So using this visualization, we can inform the NYC DEP, Department of Environmental Protection, that, hey, if you have limited resources, let's say the upper part of the Manhattan and then some part of the Bronx or Brooklyn is the good place to invest or investigate more deeply into the sources or causality of the drinking water complaint. And then now, so this one is showing NYC's data. I'll talk in terms of root mean square error, RMSE result, which means the smaller, the better fit. So if we compare, say, for example, Queens, Staten Island, or Brooklyn, it is very clear that SVM is showing smallest number RMSE values, which means support vector machine is performing better than other these three machine learning techniques. However, in terms of for Bronx and Manhattan, the random forest is consistently doing way better job in terms of forecasting, because as you see, the RMSE values for compared to other machine learning, random forest is performing better. And then we thought about the reason, and then it's most likely due to observed spikes in the training and validation data. As you see in here, Queens, Staten Island, and Bronx, the Brooklyn are consistently showing some near pseudo steady state. However, the Bronx and then the Manhattan is showing very unexpected high peaks in these three regions, in this 3 time period. So we tentatively concluded that random forest is good for reflecting this unexpected spike compared to other machine learnings. However, SVM is good for predicting in terms of a pseudo steady state observation. And also we have the communication with the NYC DEP, why these 3 spikes are there in this specific time period. They don't know that, because those are the influx of the data coming into their database. The problem solved, but the causality, why it is happening, it still bears a further examination. And this one is showing some results for Baltimore and then Kansas City. And then it turns out that SVM seems to be performing better than in terms of LMSE values. SVM is working better for both cities. So in terms of policy implications, as you all, I'm sure you all agree, but water quality database is very important for water utility operations, regulatory compliance and reporting, and then transparent and strategic use of a water quality database is very important, and also the sound capital and operational planning, and also the public health issues. Yeah, that's right. So, and then it is also useful to comparative viability of various sources of water and effectiveness of water treatment schemes, and launch water distribution system field investigations. And then deeper and broader insight into building water system performance. My personal interest is very on building water system, premise plumbing. So because the people are the actual sensors living in that building, so they can report out in real time and also the real location. So that's, yeah. So the conclusion-wise, we assess the influx of water quality complaints from 311 data, which is open data server, so everyone can access to those data. And then data analytics is another angle to fully understand building water systems and premise plumbing systems with a macro level, spatial temporal perspective. I know lots of people, very dedicated researchers, devote whole their life in understanding why the lead are detached, like a dissolved lead or particulate lead within the pipe system using experiment or the modeling. But this type of macro approach from the bigger scale, and then using data analytics is also another way to approach the same problem about the water quality issues in our water system, and also the decentralized water systems. And then forecasting of water quality complaints is very important in improving water quality operations, planning, and management. And then crucial for local officials in these affected areas to assess why so many complaints were made, and then what course of action needs to be put in place to curtail or reduce an increase in the future. That's right. So again, we solve this type of problem not just for us, but for the citizens, right? So to help the water utilities, for them to supply the water 24/7, 365, best high quality water. So that's our job. So, and then in conclusion, so these are the book that we just published it last year, Embracing Analytics in the Drinking Water Industry. All the source code, all the procedures are included in an open access. Every book, every chapter is all free available. So if you're interested, please download. And then, and also many of the co-authors, chapter authors, are also in this panel. I'm very happy about that. So again, yeah, that's all I have. So thank you very much. Okay.
Thank you very much, Dr. Lee, for your presentation and for this nice and smart way to manage this issue of water quality. While human, they can cover maybe partially the story, and they can be combined with devices for some specific water quality aspect maybe. Is there any question from our audience? Yeah, Jordi, please.
Should I stop sharing now?
It's okay, you can keep it. Maybe we need to go back to some slides.
Okay, yep, we'll do.
Yes, Thank you. I
Yeah.
have a comment first. I think it's very interesting, this study. I knew sometimes the customer complaints are used as sensors, but this is the first time I see a study like this with so large data set. So I really enjoyed. I have just
Thank
one
you.
question.
Sure.
Yes, you're welcome. Related to the 3 cities, if they were chosen because of any relation to aging of infrastructure, and I'm asking you because we did a project where we monitored, it's a bit different, but we monitored wastewater in the city of Barcelona, and we choose 3 different districts with different income ratios, so high income, mid income, and low income. And the criteria was to see if there is any difference in these districts, how they behave at home, how they use water, etc. So I was wondering if there is any also criteria in these 3 cities, or maybe it's not.
Absolutely. Thank you. Yes, that's excellent comment. Thank you so much. Actually, our follow-up study is about use of the water equity issues. So right now we're simply displaying the water quality complaints, and also we're making a forecasting model. But right now we are overlaying with the household income level, education level, and then the median housing levels, or the housing price levels. Now we're doing that in NYC, but unfortunately we couldn't find any correlation so far. But that's in the to-do list as a near future research. Yes, that's water equity. As you know, it's a very hot topic these days, right? So,
thank you.
Thank you.
One more question from the audience, John Ralston. Have you considered analyzing not only customer as a sensor data, but also combining it with physical sensor data?
Absolutely. If there's a possibility, right now we are doing this one because of the lack of, and also especially after 9/11, the data, or it's a very much restricted and in NYC Department of Environmental Protection. But fortunately, this is the only human sensor data that we could obtain. So that's the reason we are focusing from here. But eventually, we are narrowing it down to attack this the premise plumbing, or the building water system, or decentralized water infrastructure, to further deeply understand that. So if there's an opportunity using the sensors, we're 100% for that. So yeah.
Thank you very much, Dr. Lee, for your answers and interesting discussion. Let's move to the next speaker. Our next speaker is Giovanni Francesco Santanastos, Associate Professor, Department of Engineering, University of Campania Luigi Vanvitelli. He's a co-founder of the academic spin-off MidHydro. His research area includes smart water networks, contributing to the development of algorithms and methods for water supply network partitioning by integrating heuristic optimization techniques with element of graph theory. And he has also interest on environmental remediation based on the optimal design of permeable adsorbing barrier for polluted groundwater. Mr. Giovanni will give us a talk on the topological and hydraulics tools for water network partitioning and protection. So please, Giovanni.
Thank you for introduction. Good afternoon to everyone. And let me share my screen. Okay, just a moment.
So maybe we lost Giovanni. He has some problem of connection.
Maybe we can wait just 2 minutes and after maybe we can go on because we are out of time. We need to ask, I have to ask the speaker to go far on their presentation.
Yeah, Giovanni. You are muted. Can you unmute yourself?
Do you see my screen?
Yes, but
Do you see the slides?
No, the slides, no. We see only the Zoom web page. So you are sharing your screen, but not presentation.
Okay, I can repeat. Okay. Now.
Yes.
So
can you just make it in the
now you see my screen, my presentation.
Mode? Yeah.
Okay, perfect. Thank you. Sorry for the delay. So the idea of water network partitioning is based on the paradigm of divide and conquer, and in general it consists in dividing water network in sub-networks called district metered area, using flow meters and gate valves. So starting from the original layout of the network, we can obtain a water network partitioning by inserting flow meters and isolation valves on boundary pipes, and specifically boundary pipes are pipes that connect different DMAs. There are two different approaches to water network partitioning problem. The first one is virtual partitioning by inserting bidirectional flow meters on boundary pipes between DMAs, while the second is permanent water network partitioning by inserting gate valves and flow meters on boundary pipes between DMAs. Past years, the main advantages of water network partitioning are, of course, evaluation of water balance and minimum light flow, reduction of water losses by pressure management, monitoring network performance and water consumption, and protection for accidental and intentional contamination event. But the main drawbacks are the degrees of network redundancy, because traditional water distribution systems are designed to be looped, increase of energy dissipation caused by pipe closure, and the last one is increase of management cost needed to buy, install, and repair flow meters and also gate valves. In the past years, we can find in technical literature some suggestion about permanent DMA dimensions. For example, these suggestions are based on the number of inhabitants, for example, from 1,000 up to 3,000, or from 2,000 up to 12,000 inhabitants, with a length of pipe from 5 kilometers to 30 kilometers. Other suggestions are about the number of properties. For example, we can have the small DMAs with 1,000 properties, medium DMA with about 3,000 properties, up to large DMA with up to 5,000 properties. But these suggestions are based only on empirical considerations and the limited case study. So it's very difficult to apply this consideration to a large real water supply network. And generally in this context can be useful using an approach based on trial and error procedures, also combined with a hydraulic simulation. Then nowadays, several water network partitioning have been proposed in the literature to find an optimal water network partitioning layout, and they are generally divided into phases. The first phase is the clustering, and the second is the dividing. Of course, clustering phase is aiming to define the number, the shape, and the size of DMAs by minimizing the number of boundary pipes or other pipe features such as length, diameter, and so on. And balancing, and at the same time, balancing the number of the nodes of each cluster or other node features such as demand or elevation and so on. While the other phase, dividing, the goal of dividing is to select boundary pipes where to locate gate valves or flow meter in order to maintain the hydraulic performance of the system. Most about the clustering phase. Nowadays, the most used algorithm in scientific literature for the definition of clustering clusters are the graph partitioning, which is a technique of computer science developed in order to solve problems that need huge computational power, like, for example, simulation based on finite element methods that require distribution of the finite element mesh among different processors. Other algorithm is a community structure, and these algorithms are a part of the social network theory, and specifically for this kind of algorithm, a network division is good if there are many edges in them. The last one, the other one is the spectral clustering, which is a technique which exploits the properties of the spectrum of adjacency matrix and the Laplacian matrix of the network graph. And it is proved that spectral clustering provides an optimal solution to the problem of minimum cut set. While for about the dividing phase or physical partitioning, which consists in defining the best location of flow meters on boundary pipes, some procedures are proposed in the literature. For example, iterative methods or optimization techniques that minimize the cost in terms of flow meters or installation cost and hydraulic performance deterioration. And then in this context, Bedrider spin-off offers an innovative solution software called SWAMP, a software for smart water network partitioning and protection. SWAMP is software based on geographic information system. It calculates innovative local and global performance indices to evaluate and compare different layouts of water distribution network. It can compute network partitioning based only on topological information without the availability of a hydraulic calibrated model of a network, and also it provides multi-scenarios analysis for optimal positioning of water quality sensors. Additionally, it can generate automatic report as output, and also it can provide a decision support system for water utility. The software can be accessed online with a username and a password via the following link: swamp.net. So in this slide, we can see the main SWAMP GUI, where it's possible to perform the hydraulics analysis. Then we can see now the section in which it's possible perform clustering analysis specifically, because we can design the water network partition in a real system. The workflow is based on two sequential phases. clustering and partitioning. And specifically in this slide, the graphical results of clustering phase can be seen. Node belonging to, say, the different clusters have different colors, while the boundary pipes are highlighted in red, indeed. This slide also shows the results of partitioning phase, specifically in the square image, the location of flow meters and isolation valves on boundary pipes can be observed. Since the partitioning phase is an optimization phase, we can compare the solution with different number of flow meters obtained with different clustering solution. In this example of Pareto front, with using as clustering algorithm, multi-level recursive bisection in blue dots and edge between a community in orange dots. Then we can, in this last slide, is reporting a sample of calculation of performance indices. Okay. In this part of the slide, we can see the hydraulic performance indices computed for all points of Pareto front. And in addition, it's possible to compare a specific water partitioning layout with the original network layout. And also this result can be downloaded as a CSV file for further processing. So thank you for your attention.
Thank you very much, Giovanni. Thank you for your presentation. We will just maybe take one question from the chat. Are there any information on the average flow, average flows during the day in a typical DMA?
Yes, we have the possibility to analyze a single DMA. Also, in case if you want to visualize the variation of the flow inside a single DMA, and the results can be extracted by performing by computing a performance indexes. Because we can compute performance indices and all the performance indices with also indication of flows inside each DMA can be extracted by the software.
Okay. Thank you very much, Giovanni.
Thank you too.
I would like to thank all our speakers for this first session. Time maybe to move ahead for the second session with Jordi.
Thank you very much, Abdelkader. I have just an advice for the speaker. We are really out of time, so I have to ask to all the speakers to keep the time for each presentation, so we have also time to finish our workshop and to have a little time for discussion. Thank you very much for the collaboration. Nicola, the floor is yours for the second session.
Okay, thank you very much, Anna. Yes, this second part is dealing with innovative water quality monitoring and control. And we will listen from 3 different speakers about different topics. The first one, Luca Sanfilippo from Sistea. Luca is actually a senior consultant about environmental monitoring. He used to coordinate and manage environmental instrumentations project, dealing even with water quality monitoring and analysis. At the time being, he's working on environmental monitoring and control systems. He is cooperating with Sistea as project coordinator and marketing manager. And he will present in the topic dealing with innovative water quality devices. We will listen about the maximum allowable values we will listen about the way to control of punctual pollution sources which is requiring online water quality monitoring. Definitely exist automatic analytical tools for online water quality monitoring, and Luca will tell us how to monitor a wide range of chemical and even biological parameters. Please, Luca, start your presentation. Thank you.
Good afternoon to everyone. I will try to share my screen now. Do you see my screen?
Yes.
Yes.
But I don't visualize here. Full screen. Where can I start the presentation? You know, because there is always, sometimes I have on the bottom the start. Here. Okay, good. Sorry. So, okay, my presentation is concerning innovative water quality monitoring devices. And as anticipated, I want to tell you in the back now that the most of the water quality monitoring market is managed by the requirement of maximum allowable values, which are the values that there should be followed, not to overlap some threshold levels, no? And so the regulation in each country require for a different kind of water sources, which are the limits. And so according to the limits, there is the need to do monitoring. Of course, the monitoring in the general sense is also monitoring when you go and collect a water sample on monthly basis, then bring in lab and do the measurement. Of course, the monitoring become more consistent when, of course, there are more data, and when there is the need of collecting samples more than one per day. Usually this is very difficult then to perform during the measurement lab, because even the collection operativity, when you do 2 or 3 samples per day, is practically impossible. No one is using this. And so when you have the need to measure more than 1 or 2 samples per day, then there is the need to have an online monitoring. So according to a review done many years ago, usually, for example, for a nutrients analyzer, so the analyzer that measure ammonia, nitrate, or phosphate parameters, the requirements that are requested by the users are usually a long-term unattended autonomy, a certain compactness, a low reagents and sample consumption, a low life cycle cost, an excellent reliability, an easy interface with data logger to send the data somewhere, and low maintenance by non-expert users. So this is a main requirement for this type of analyzers, but also for an analyzer to measure wastewater treatment plant, more or less is the same, or a sensor. Here in my presentation, I don't speak about sensors because our company is specialized to automate methods based on different type of analytical methods that are usually done in lab, but usually then can be applied also for an automation. So what is our main expertise is wet chemistry spectrophotometry that can be applied to measure a wide range of chemical compounds. Other analyzers are based on fluorimetry, and fluorimetry is also used actually in the last 10 years to measure with sensors, so small. In this case, we can speak about sensor, small devices that, for example, can now detect even very reliably hydrocarbons or chlorophyll in water, or, for example, a method that is widely applied for seawater analysis to measure ammonia in fluorimetry that use even a reagent. So that means is a wet chemistry method. Then there is the wide range of applications of the UV absorption directed methods that mainly are that is mainly used to measure organics, nitrate, and color, and other parameters. And the next speaker will probably speak widely about this type of analytical method. Then we have potentiometric-based methods that use electrodes, but not just direct inserting them. So in some cases, inserted directly in the process. In other cases, managed by a fluidic analyzer, in order to be much more accurate and constant in their data output. Then there are type of amperometrics that even is a kind of method that use a sensor. Is amperometric sensor typically now very well used in drinking water monitoring networks for the measurement of free or total chlorine, or are even methods for other particular compounds like cyanide, and even stripping voltammetry. That is a particular application of amperometry in which is possible even to detect metals. And there is a wide literature and research working with the stripping voltammetry, even and voltammetry for detection of other parameters using biosensors that are based on screen printed electrodes. So, for example, in this picture, I show an amperometric sensor that is integrated in an analyzer to measure cyanide that use also a dialysis tool. The dialysis tool is an introduction for the next screen, where I show that sometimes in this type of applications, the preliminary treatment of the sample is very important. And so the main treatment.
Luca, sorry, 2 minutes left.
2 minutes left?
Yeah.
Incredible. Okay, so these are the typical methods that can be used for to pre-treat the sample. Anyway, sorry, you could do the same even for the previous speakers, not only to me, but anyway, now I'm here and I'll try to manage. Data output is another of the requests that is requested by the users, and now there are a lot of type of data outputs and serial communication protocols. This is a short list of methods that can be available actually in wet chemistry online analyzers. And you see there are a lot of metals, inorganic ions, and other type of chemicals. This is a typical example of an analyzer, wet chemistry based, that is measuring COD using a wet chemistry method and a spectrophotometric method. This is an example of integration of different type of methods that is based on pH, that is amperometric, that is potentiometric, nephelometric method to measure TSS, and direct reading method to measure organics in one single analyzer that is extractive. This is an example of a compact wet chemistry analyzer that is integrated in a probe to measure nutrients in fresh and seawater. And this is a particular integration of two types of analytical methods, spectrophotometry and fluorimetry. This is a layout of analyzer that is made in a portable way. We named even benchtop. And this type of analyzer is applying an analytical method to measure cyanide using an amperometric sensor. So this is showing that that are real applications, the real commercial products based on this type of technologies. The last example I would like to know, the first and the last, is an analyzer to measure in voltammetric method, lead and cadmium. That is a new product that we are improving. So using a type of digestion for metals and then stripping voltammetry in order to measure at a low concentration, I mean some ppb, cadmium and lead in the same unit. This is an analyzer to measure total coliforms and decoli. So now we are speaking not more of chemicals, but biological parameters. Is an automation of an analytical method that is also an ISO method. And it is a tool that can control biological parameters, very important for drinking water and potabilization in automated way. And okay, this is the layout of the analyzer as it is. So the conclusions is that now actually to control these threshold levels in any kind of water, there are a lot of analytical tools automated that of course can have some limitation. There it is, as already anticipated in a previous speaking, also quite high cost, but can provide accurate and reproducible detection of a lot of parameters. So in case you need any additional information of this short view, we can visit our website, and I thank you for the attention. Bye-bye.
Thank you, Luca. Thank you very much indeed. I am impressed about the number of devices you have in your catalog, let's say. And of course, putting the cloth of someone managing water services, of course, thinking about an online monitoring devices like the ones you shown by treatment facilities or by a control section along the distribution system, of course, it could be difficult to find the right place, let's say. But I think in the forthcoming time, maybe working on kind of devices being more smaller, let's say, in order to maybe to be put inside manholes, whatever. But of course, it's I recognize it's quite difficult. I am impressed also about
the problem. The smaller sometimes is not fitting in actual technology with the accuracy that is requested to achieve the control of these levels, of these thresholds.
But maybe
quite low.
It could be enough for the purpose. But talking about the last slide you shown, talking about the monitoring of bacteria, I wonder if you had to face with problems sorry, in terms of concentration of your sample, because of course I recognize that the device can work if you can put the water inside the device, but of course the sample could be not representative of the whole, let's say, water matrix. I wonder if you think about the possibility to concentrate the sample before to inject water inside
this analyzer is based on an ISO method that is based on a very well-known method to detect bacteria in water that is named ColiAlert 18. This ColiAlert 18 is based on samples that are 100 milliliters, so there is not small samples. And so even our bottles where is based automation are based on the same quantity, that is 100 milliliters. So with this analyzer, it's possible to detect either the presence absence of bacteria after, of course, a long incubation, that is 18 hours in 100 milliliter sample, or even to have the semi-quantification statistical of the quantity of bacteria colonies either total coliforms and Escherichia coli in a kind starting from 100 milliliter, using a certain kind of statistics that use the smaller cuvettes. That is even done in the same ColiLert 18 device method, using a particular device that is named ColiLert QuantiTray, that can calculate, estimate statistically this quantification of.
Okay.
So in this case, there is no need of concentration. Why could be in other methods, for example, to measure ATP, for example, there is the need of concentration.
Yeah, clear. Thank you so much.
You're welcome.
I can't see any question from the chat, and therefore, if you agree, we can pass the floor to the following lecturer, which is...
No, sorry, there is one question.
I didn't see.
It's only this asking that does include dissolver and the lead remaining at the metal surface. It is possible with this type of methods to measure either only the dissolved part and either the total, total lead, using a particular digestion, working on the sample that is not filtered, of course, because if you filter the sample, you measure only the dissolved ions which are in water. While if you don't filter, or you filter at a certain cutoff, we use for the total ions a cutoff of 100 microns, that is not very high cutoff, it is possible to digest the water sample and so even measure the ions that are on the particles. That means after digestion, they are dissolved.
Okay, great. Thank you so much.
You're welcome.
I'm going to introduce the following lecturer, which is Jordi Reich. I don't know if I pronunciate correctly the surname of Jordi. Anyway, Jordi he has a PhD in environmental analytical chemistry, obtained by the University of Barcelona, has more than 15 years of experience in water industry. And Jordi is going to show us a specific spectrophotometer, which is SCAN. SCAN, as far as I can remember, is an Austrian device which has been developed by, if I remember well, Andreas Weingartner. I don't know, Jordi, if you met him before. I did, and I had the opportunity also to deploy a couple of scans in drinking water and in wastewater. And therefore, I can't wait to listen what you are going to say us about online monitoring of drinking water networks from innovation to real application. Please go on, Jordi. Thank you.
Okay, thank you very much. Hope I don't disappoint you. Thank you for the invitation to this workshop. Today, I'm going to talk about SCAN, but also will explain you that we are now part of WATERSET. And first, let me explain you a bit who we are. We are a company innovative in manufacturing, flow measurement, water quality, and control products for all the water utilities, municipalities, etc. We are close to 120 years of operation, and we are a large company with the headquarters in USA, but present in many, many countries, with 9 manufacturing sites and 5 R&D centers, showing our vocation towards innovation. What we aim to provide in WATERSET is different solutions to control quality and quantity from the water we are using in the catchment of the plant, through the different treatments in the plant, and then also in the network when the water is supplied to reservoirs, but also to buildings, and even in very far areas of the distribution network, like endpoints or remote areas. For that, we combine, as I said, products for quality and quantity, but also for for communication and visualization. If we look more in detail, we provide electromagnetic and ultrasonic meters that we have been producing for many years. For water quality, we also provide many different systems that I'll show you in a while more in detail. And then the communication is with cellular endpoints that we can use, that we have been deploying now also for years. And finally, software and analytics, so all the data can be visualized and we can track water consumption, but also get insights on the data we have and improve our operation. So as you said in my introduction, we are ESCAN, we are part of Badger Meter. ESCAN, as you said, was the owner was Andreas Weingartner, that I had the pleasure to work with for many years. And now we, and together with ATI, we are part of Badger Meter. ATI is a company specialized in producing sensors, electrochemical sensors, and we, as you know, are more specialized in producing optical sensors. So it's a perfect match to be able to provide good solutions in many parameters. In ATI, for many years, one of the topics that was kept in mind in the innovation department was to be able to offer solutions that are not dependent of power supply. And through the years, this solution was developed, which is a solution using ultra-low powered smart and digital M-node sensor technology, so that you can have these systems either in a fixed solution or a mobile solution, modular systems to plug as many sensors as you wish for water quality, of course, with a certain number of parameters, and that you can monitor without the need of a power supply, so with an autonomous battery solution that you have. In ESCAN, another topic that we kept in mind also was the water scarcity, there's no need to discharge water when we monitor, so there's no water loss. And we developed this, what we call pipe scan system, which is a system that we can place on top of a pipe in the network, and then the water is entering our solution, flowing through the different chambers and going back to the same pipe. For that, we have a nano pump that is helping, and as you said, and previous speaker as well, we have different sensors, electrochemical, but also optical, based in UV or UVBs. And for these sensors, we have automatic cleaning, like this brush that you can see here, to try to keep maintenance as low as possible, and to offer this solution where you can monitor turbidity, chlorine, conductivity, pH, organic carbon, etc. So in here we see how this system look in the real case. So moving from innovation department and design into the real application, you can see pipe scans being installed in different pipes of different dimensions and materials, and also the aquametric being installed in different locations. And in some of them, as you can see here, being very remote. But as you all know, also in these maybe areas at the very end of the network is where you also have more quality episodes because of lack of chlorine, etc. And therefore they need, of course, to be properly controlled. So when you have a system like this and you can deploy sensorization in the network, in the plant, etc., you can then see this kind of situations that I show you here, where we can see on the left different parameters of the water leaving the drinking water treatment plant, where in this case there was an event affecting free chlorine, UB254, and dissolved organic carbon. And on our right, we see the same water that was leaving the plant a few hours or before. And the
Jordi,
same.
1 minute left.
Okay, and the same peaks, of course, with much less intensity, but we can, with this proof that we can control the water since it's being produced, treated until it's in the network, in the city center, or in a reservoir, and we can validate then also our hydraulic models. We also can see, when we deploy many sensors, we can see and detect events. In this case, I show you a turbidity event that was happening when a pumping station started to operate that was not planned to be, and then how it affected turbidity and how it took a few days to turbidity to recover to normal values after this event, that the utility could keep control of it. We are also innovative and open to be able to integrate solutions that we don't manufacture. For example, when we need to also provide, in addition to physical-chemical properties, we need to provide a solution for microbial monitoring. We are open to integrate other brands, other manufacturers' solutions, and we integrate it in our hardware, but also in our software, so that all the data then it's transferred from our system with all the data analytics to the end user. And so finally, I can say that with all these solutions, we can provide a good compromise for the water safety plans to have water under control, but also to have a good security approach. You know that in US, two words are used, while here sometimes we only refer to safety. In Spanish, we only have one word to say safety or security, but you know these are two different concepts. And in case there would be a accidental or intentional contamination, we need sensors to detect it fast and be able to react fast and take decisions. So this sensorization is also helping in this way. So that's all from my side. If you have any questions, we can talk now or maybe later also by email. Thank you for your attention.
Okay, thank you very much. Indeed, I don't know if there are questions about the nice presentation you gave. Otherwise, I can introduce the following speaker, which is Sergio Martinez. Sergio Martinez is a technical engineer. He developed embedded electronic system and wireless communication for critical environments. Since 2011, work at Leitat, the company where he is now, and where he provided comprehensive solutions to clients based on the development of intelligent systems with embedded software and with data image processing. At the time being, he is leading the business area related with artificial intelligence and software engineering. He will tell us about research of smart devices. And please, Sergio, go on with your presentation. Thank you.
Oh, thank you, Nicola. Can you see the screen?
Yes.
Okay, thank you for the introduction. Thank you for the invitation. I will try to provide you a very brief explanation about what exactly Leitat is working on in the field of research in water quality, water monitoring. So the first thing to take away is Leitat is a RTO, a research technology office. So mainly we are a technological transfer agency. We are a non-profit, and the leitmotif for my institution is to transfer the knowledge to the companies, to the industry, in order to create a more confidential world. So mainly this is some numbers from my institution, very fast and very quick, but the idea is we are 50-50, so we are almost in parity in gender equality, and we have more than almost 50 million of revenue in 2021. I will try to go faster on that because I suppose that the slide will be shared with you all. But mainly we have three main areas of actuation. The first one is the intelligent development. The second one is the human development, and finally the sustainable development. And all of them are trying to work together to flow in order to create a positive impact to the society. So mainly from my point of view, like a technological stuff, there are some different agencies in the field of water quality and the water monitoring. The first one, principal for me, is the water scarcity. Okay, there is a high problem with that. There is an increasing figures on the water consumption due to the growing of the population. There is high energy costs in the treatment of the water. Finally, we have a problem with non-revenue water, that is the one that it's an origin but never reach the destiny. So from a technological point of view or from a societal point of view, we have three main challenges that are they use the water more effectively, minimize the treatments, minimize the cost, even in time, even in energy costs and resources. And the third one is the distribution. It's important to distribute without leaks. Over there, there is some political guidelines, some political best practices that we need to follow up in order to reach the Sustainable Development Goals. So there are some different Sustainable Development Goals that are related to the water quality, with the water monitoring, with the water itself. So it's important to be compliant with the EU and international and national legislation. So mainly, as I laid out, we plan to provide a holistic overview, a holistic approach, trying to use a single technologies working like a silos. Instead of that, we plan to provide a cooperative environment where different technologies, for instance, photonics, for instance, additive manufacturing, artificial intelligence, electronics, can work, can meet together, and can provide some kind of extra added value solution. So now I go to the point. Okay, what we are working now in LETAT in terms of water quality, water monitoring, and in general in the water sector. Okay, the first project that I want to show you is one related with the water pipeline inspection. Okay, let's see if it works. Okay, apologies because it's not in English, but I will try to explain you in the meantime. This is working. Okay, the main idea behind it, we have a water utility here in the region, in Catalonia region, that used to perform inspections, visual inspection of the pipes, of the water pipes. They have a problem that the solutions that they are running are out of date, are not operative, and mainly they have tools from one use. So they come to us and say, okay, let us how you can support. And we say, okay, maybe we can design something using additive manufacturing, okay, and using a handmade design for you that maybe can support your inspection. So the first thing that we do is perform additive manufacturing study, a mechanical design of how the system should to be. And after that, we put some electronics and we put some camera systems, some imaginary, in order to have some data collection. At the end, we put some artificial intelligence algorithms over the data collection, and the idea was to provide real-time decision, real-time inspection, real-time monitoring of the pipes. So at the end, nowadays is a solution that is currently running in the Barcelona area. Okay, and they have a solution that is fully operative and it's fully working. And the most important thing is that it's usable, because sometimes the operator, the person that is working in the field says, okay, I don't want the technology. So the idea is to use a technology that can be adaptable by the users. Okay, here you have some pictures how the system looks like from a user point of view. So it's allows an easy inspection of the pipelines. Okay. Okay, the second thing that I want to show you is it's not only a matter of technology, it's a matter of stocks, it's a matter of proprietary bases. Okay, you have some tools in order to monitor your water quality, you have some pieces in order to perform some activity, you have some pump, you have some whatever. Okay, sometimes when it's broken, You need to go to the manufacturer, ask for that. Okay, wait a time, pay the invoice, blah 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 blah. And sometimes the replacements are very, very expensive in cost and in times. So the idea was to create a catalog of digital components, okay, and create a digital twin, not a digital twin of the water or the cycle, instead to create a digital twin of the piece. Okay, so in this term, we support the company by creating digitalized pieces, digitalized components, and training them about how to manufacture by its own this piece. So in terms of when the piece is broken, we have a day zero, a replacement of the piece. With the data that is generated by the different operators as well, over that we run a predictive maintenance of the piece, of the engine. So at the end, it's not only we are able to replace the piece when it has been broken, instead we can planify when a manufacture need to be done and when a repair, a substitution, a replacement need to be performed. So at the end, it is a data leak at the time. At time zero, we can avoid that.
Sergio, 1 minute left.
Okay. Okay, the third project that I want to show you is a project for aquaculture, where one of my problems is the problem of third-party components. You put a sensor, you need to provide, you need to buy a license, you need to buy a software, you need to buy the sensor itself, and sometimes it's very hard to manage from a whole point of view the aquaculture system. So the idea was to create a middleware in order to provide a data software, a data space, in order to allow a very easy integration of components and to reduce operation costs. And the last one that I want to show you, I am going very fast because I know that we are out of time, even if it's not my fault. Okay, but sometimes when you are the last one, you need to pay the price. Okay, but in any case, the last one that I want to show you is the Astral sensor. Okay, this the Astral Analylia. This is a microplastic sensor. Okay, because one of the problems that currently is facing the European Commission and the member states is that it's mandatory to measure some pollutants, especially the emerging pollutants. Okay, for temperature, for chlorophyll, for pH, there is a lot of tools, but for innovative pollutant, there is no tools, and you need to go to a lab. Even in some of them are not a reference standard methods to measure how, the microplastic, for instance. So we were working for a long time to provide a combination of electronics, photonics, artificial intelligence to provide a tool that will be able to measure online microplastics. So here you can see a simulation on a lab, okay, using a semi-filtered data. Okay, in order that we have no inference, we only have microplastic and waters, and we are able to measure 300, 400 micrometers particles in real time. Okay, it's a portable device you can see on the left side, and the idea is to provide to companies, but especially to research institutions and aquaculture institutions, a portable device that can support them to measure microplastics. That, as you know, it's one of the trending topics around the world about pollution.
Thank you very much, Sergio.
Okay.
I can see there is a question from the audience, and particularly the question is dealing with the pipe inspection tool, and they are asking which data are generated, it may be qualitative or quantitative, and if the device can be used in the meantime the pipe is in operation. I think a big issue is to inject and to recover the device at the end.
Yeah, in fact, it's a good question, because need to be used when it's in operation the pipeline. Otherwise, the fluidic system that is used to impulse the device is not working. Okay, we need to move water in order to move in advance. Need to be recovered by the humans. This is true, but the operation to advance is done by fluidic movement, by move the water that is in line. So the pipeline need to be in operation, need to be a lot of water there. And in the first prototype, it's only qualitative data. It's an image, it's a stream of video, and the human is working, watching the video and say, okay, it's stacked or not. In the second version that we are currently working, we are including artificial intelligence in order to provide autonomous decision, autonomous information to say something is broken, something is ready to be broken, but as well we plan to integrate, we plan to include some extra information, for instance, to include turbidity or colorimetry in order to say something that can be wrong or not. In the meantime, you are in the inspection of the pipe.
Okay, thank you very much. I think we have overtaken our time available, but I don't know if there are other questions. Personally, I've been impressed about the data repository about the three-dimensional printers and spare parts, whatever, and maybe I will ask you later where to find the model and how many they are and whatever.
Okay. Whenever you want, this is important maybe for you and for the community. We are leading the Digital Innovation Hub in Catalonia about additive manufacturing. And we are leading a hub in additive manufacturing as well, with some manufacturers, with AP, with Renishaw. So we have a lot of engineers, we have a lot of machines. So if you have some kind of project, including additive manufacturing, we are definitely an expert, but because we have an ecosystem in our institution with a lot of big players on that.
Okay, thank you very much indeed, Sergio. I think maybe Anna or
thank you very much.
Or Armando wants to spend a few words closing the session.
We have to introduce Andrea Rubini that will close the session and start a little bit discussion about all the things that we heard today. So Andrea Rubini, the floor is yours. Thank you very much to all the speaker and the moderator. Now Andrea Rubini will start his discussion.
Thank you so much, Anna, and thanks to all the speakers. I mean, this afternoon we went through, a lot of interesting topics discussed by the speakers. And I mean, I myself, I'm a water resource engineer, but at the same time, I understand that the digital world is becoming, is already such a large environment in which you really need a lot of knowledge and expertise is needed to carry out and to find new innovative solutions as much as the challenges advances. Now, my point as Water Europe, by the way, I'm the director of the operations of Water Europe. As you know, Water Europe is the European water technology platform, and whatever it is around water and whatever is around innovation for water falls into the interest of Water Europe and its members. But when we go to the digital transition, when we go to what is in Europe the twin green and digital transition, then we have really a world that opens in front of us. But at the same time, water is now under the spot of the European Union, is under the spot of the United Nations. Recently, the United Nations World Wear Report has been released a few days ago, and there is much more than a concern about water availability. And what is important is that we are all now aware of the matter that water represents one of the planetary boundaries for which we have limits to exploit this resource. But at the same time, we find ourselves in front of a situation which is much more concerning, especially when you go to water scarcity or when you go to pollution of water resources. Now, we know the challenges. Let's say the challenge is being able to manage water efficiently in order to avoid that water becomes scarce and become polluted. Then in the end, I mean, water scarcity, it is not only because water it is not enough, but because water could be polluted or water is too much. If you think, I mean, to the floods, in a flood situation, water is scarce. I mean, the water that we need becomes scarce because then it's too much polluted. Water might be scarce also because it's underinvested, because we do not invest enough money, or because we lack of the capacity of making choices that are not any longer belonging to the concept of the linear approach of the exploitation of the resources. And for water, thinking that today we can still work on a linear approach, which means take, use, and dispose, it is completely out of question. So we need circularity, we need new solutions to make this possible. Of course, digital solutions represent the real new frontier for water management. Now, we know the challenges, but I mean, and we know also the pressures, because the pressure is the matter that if you read, I mean, the recent report, it was published in March by the European Union on water scarcity in Europe. We have 3 countries in the Union which are in a very already difficult situation, which is Italy, Spain, and France. That's because of climate impact, because of climate change, because of a number of factors that across the years, I mean, the past 20, 30, 50 years, took us in a trajectory which is not sustainable any longer concerning water management. Now, I ask him into the speakers, in one sentence, what is the opportunity? What do you see as an opportunity from the digital domain? How this can contribute effectively to solve the water crisis today? It's a question that I raise, I mean, to all of you, one by one. Really, I need you in a powerful message. What is your opinion, the contribution of the digital domain, or particularly, I mean, of the capacity of creating instruments able to monitor water? What is, I mean, the contribution that can be given in a short sentence, really?
It's complicated. Maybe I can try to start. For me, the most important impact of digitalization is 2 fields. One is the democratization of the access to the technology. Okay, because nowadays there are different technologies, different countries, so it's supposed that in some time the digitalization will be equal opportunities for all the countries. And the second one for me is the opportunity to impact in a societal impact to the humans, especially in terms of awareness, in terms of to make conscience about what exactly the problem is, because nowadays there are problems that are not existing because we cannot see. Even that the digitalization will provide the tools to say to the population, okay, we have a problem, you can see the problem and you can act. So it will be a powerful tool to increase the awareness of the people.
That's a very good point. Thank you. Who else wants to contribute?
I can say something.
You're welcome.
Digitalization will not make rain, but will improve management of water.
But then, in a way, it will contribute to make rain if you are able to manage water in a way that we impact less a bit on the planet.
Will not make rain in the sense that the problem will be there, but if we improve management, that means that we will use less water, we will reuse much water, and we will recycle as much water as possible.
Somebody else wants to add comments? So I have another question, maybe the last one. And what do you see, I mean, as the main barrier for the deployment of digital solutions for the water sector? Is it a matter of investment? Is it a matter of legislation? Is it a matter of capacity of the society to make the change? I see that Abdelkader raised his hands.
Yeah, I think the level of investment is one of the priorities and the key question, because this is what is making barrier for most of water utilities to adopt technology that can optimize their operation and production, etc. And the second one, I would say the resistance to the change, because most of the water network and systems, they have been operated in some ways since a long time. So if you want to implement some new solutions, I think it's clear that there is some resistance, where there is a need of making more awareness and maybe some more education to the people concerned by this change. So this is what I can say in few words.
Thank you very much. So it means that for sure, I mean, the matter of, I mean, money matters, let's say. But on the other hand, there is also maybe, I mean, better involvement of the users, of the citizens, of the final users, whoever it could be, in order that they can take part, I mean, to the decision making process, and that this may also foster the allocation of more additional funds, I mean, or additional investment for the water sector.
Yeah, sure. So I think even the end user, ourselves, I would say, we are not out of the loop. So we are part of the image. And if we track our behavior in the water consumption, and we see how much we can contribute for saving water, for keeping water as good as possible. This is another axis also where the society can help the service providers and the technology people to go together, because it's multi-phase problem. It's not the responsibility of one entity or two. So it's all the society is concerned by it.
There is another answer from the audience, which is, I can read it. It is a hard question, but I try to answer according to my experience. It's something that's really needed in Africa, for example, where some countries are still left behind in technology. So how are they going to use the digital monitoring system if they do not have updated technology yet? Africa really needs help from the system, but again, of them are still behind. Is there any suggestion for African countries? Well, I mean, I myself, I mean, I'm not a wizard. I don't have, I mean, an answer for that. But for sure, what I think is, I see water as a global challenge that must be solved locally, because at the end of the day, water is it is restricted in a local environment. We cannot, usually we do not transfer water for very long distance, like it happens with energy. So then in the end, I mean, water represents really a local issue, is a local challenge, and can be addressed locally. But at the same time, which the outlook of the global challenge of water scarcity. And of course, I mean, with different characteristics. I mean, if we move from Europe to Africa or to Asia or to the Americas. But I do think that, I mean, Abdelkader is right when he says it's nobody should be out of the loop. I mean, it's a common responsibility, but at the same time, it's also a matter of having enough investment be deployed for a sector which it is characterized by aging infrastructure. It is characterized by difficulties in the return on investment and so on. But at the same time, I do think that digitalization might save not only water, but might save money at the same time, against, I mean, the more traditional system for water management. For sure, it's a matter of changing, of making the change, not only by the individuals, but also by who manage the water, which is important. At the same time, I mean, making pressure in order to have this precious resource always in the top items of the agenda of the sustainable development, which is the same, I mean, wherever we go, from Europe to Africa or to Asia or any other part of the planet.
I can
Sergio?
add just
No, I want to remark that.
Yeah.
And I wanted the opportunity, and there is an African proverb that says, if you want to go fast, go alone. If you want to go far, go together. I think that this is one of the main barriers that we have nowadays, that in different countries, in different continents, in different sectors, citizens, water utilities, political, legal, we are moving on like a silo, like an independent institution, like independent movement. And as you say, this is a global issue, it's a global matter. So we need to go all together, because the water scarcity is something that we need to recover as soon as possible.
I fully agree, and I do hope that there will be more understanding, I mean, of the urgency on working on water, because this is also something that governments and international organization must really take the responsibility to take action, because the cost of the non-action or the cost of inaction is already high, it's already unbearable. And really, I mean, looking at this, the last report, I mean, of the European Union on water scarcity, what I see, I mean, is the pre-announcement of a catastrophe. I mean, really, there is no time left, I mean, to without taking action. I don't know if there is any other comments, I mean, on well, otherwise, I mean, we're a bit behind the schedule. I would like, I mean, to give back the floor to Anna.
Yes, I saw that there is another person that wrote on the chat that told Mr. Rubini, I put my view on your first question about the technological intervention in water distribution system. We ensure quality parameters to end user. Further, like quantity and operational parameter, we make our system more efficient one. This is another comment to your first question.
Thank you. I mean, it is also it is at the end of the day, I mean, from water service perspective, water needs to be provided, I mean, in the right quantity, in the right quality, at the right time.
Yeah,
because of time, I mean, it's important because of the right time. Otherwise, I mean, if it arrives when that is not a quality service, but also an affordable price. I mean, something that's affordable for the society and for the individuals as well. So I think that I mean, these are the perspectives, I mean, of ensuring sustainability for the water sector.
Yeah. So we are really out of time. I would like to thank you to all the speaker, moderator, the audience. Thank you also to Water Europe and to you, Andrea, for your activity with our action group. As Abdelkader wrote in the chart, we hope that we can continue this kind of meeting to generate action toward the clean, safe, and cost-effective water for all. I think that this can be our hope for the future in this kind of activity. So thank you very much. I don't know if Armando or Jody would like to add something more to.
Thank you for your participation because we have many minutes after the deadline. So thanks to all and Robin and Water Europe for this opportunity. Thanks.
You're welcome. You're welcome. Thank you, everybody.
See you.
Thank you very much. Thanks a lot.
Bye-bye.
Thank you. Bye.
Bye bye.
Bye-bye.
Thank you very
Thank you very
much.
much.
Bye bye. Bye bye.
Bye.